Hello! In this episode of Finno-Greek machining, we are going to make the rotor for this rotary vane compressor. Well, it's although it's accurate, it has to be made accurately. It's quite simple to make. Although, let me show you. So here is this rotor. Well, this is an animation about that. And now what we have here are these. There are two parts where it's bared, the bearing surfaces, and then we have a thicker part here which contains grooves for this rotor. And yeah, it will be rotating like this inside the cylinder. And well, again, I will attach a little bit of animation right after this to explain how it works. Well, you might have seen that before, but it's a little bit different. So anyway, this is what we are going to do. The round parts we are going to make in the lathe, and the grooves, of course. It will be a slitting saw operation in the milling machine. Well, let's put this away. So, first the animation, and then we go into the work with the lathe. So let's start. Here you can see the rotor and the vanes that are sliding in the slots. The rotor and the vanes are surrounded by a cylinder. The vanes divide the gap between the rotor and the cylinder in 6 compartments. Because the rotor is asymmetrically placed, the compartments have a different volume depending on their rotational position. This difference is used to compress the air in the compartments. The air is taken in when a compartment has its largest volume. The compressed air is let out when the compartment has its smallest volume. The compressor is lubricated with oil. There is a gear pump to take care of the oil pressure when compressed air is not yet available. The oil enters the compressor through this pipe. Please note that in this animation the compressor is turning the wrong way around. The real thing will be turning the opposite direction. The oil then goes through this hole in the bushing. There is a groove that allows the oil to enter under the vanes. The vanes are hydraulically pushed against the cylinder walls. Oil reservoir is under air pressure, and after some air pressure is gained, the oil pump is no more needed. The opposing slots are interconnected by holes through the rotor. This shortens the road the oil has to take when the vanes are moving. Well, that's all about this animation. Next, the material for the rotor. My steel arrived. Well, this is S355 cold rolled steel. It is better than mild steel, but not much. It is good enough for this application. I use copper packings between the jaws and the workpiece. They are not to protect the workpiece but to give some flex to it. They also make a better grip on the unmachined surface. Dialing this roughly in to avoid excessive vibrations. The top surface is different in this stock, so I peeled it carefully off. Since I am such a chicken, I only advanced the feed but kept the shallow cut. I realized that this will take forever, so I started taking deeper cuts. I was not able to get the chips to break, so I ended up having a lot of spaghetti in my bin. For the last cuts I used this insert. I have learned that it has to be run slowly with cutting oil to get the best surface finish with milder steels. This insert has weak cutting forces, which helps a lot when taking the taper out of the workpiece. Peeling off the first layer took half an hour to finish. Here I am taking the taper out of this workpiece. First I measure the workpiece from several spots and map the differences. There is a 0.1 millimeter taper within this workpiece. I measure the travel deviation instead of measuring the tailstock movement. The measurement must be done from the backside of the workpiece. The deviation should match the mapping I made. Well, it does. The tailstock is adjusted sideways until the deviation is still to the same direction, but only half the deviation it was. By measuring the travel deviation, the adjustment is spot on with only one go, instead of the trial and error involved with measuring tailstock movement. This is because the pivot point of the workpiece is not exactly known, and measuring the tailstock movement does not give exact result. It takes half an hour to finish this cut, so trial and error is not a good option here. The goal diameter is 43.95 millimeters. It is 200th undersize, which is alright in this case. Well, more importantly, the taper is practically gone. Now turning the features at the oil pump end of the rotor. The diameter is reduced down to 14 millimeters. 1 millimeter cut is too much for this insert, so I reduced it to half a millimeter. Now finalizing the 14 mm bearing surface. I use low speed and low feed to achieve acceptable surface finish. Facing the shoulder of the rotor. Slow speed, slow feed, and a very shallow cut. gear has an 8 mm hole, so the end of the rotor has to be machined accordingly. Wow, it is a very good fit. Well, it's working actually. It's here. I put it inside there, and yeah, it's a very tight fit, maybe too tight. Because now when I tighten the bolts, it becomes a little bit stiff. Uh, uh, well, it can be that, but I don't like the idea. So I will look where we need some tolerances here. Okay. That's all for this episode of Finno-Greek Machining. Ah, in the next episode, we will be making the grooves and a lot of holes through that rotator. Well, that will be in the next episode of Finno-Greek Machining. Till then, bye!